This video is to give you an introduction into how to solve problems with conservation of momentum concept in two-dimensional collisions. So here is an example. So any two-dimensional problem should be approached as two one-dimensional problems. So you apply the concept once to the x-axis and then once to the y-axis. So with conservation of momentum as well, we're going to apply the momentum conservation equation to the x-axis and then again look at the momentum vectors on the y-axis and apply the equation. So here is an example problem from WebAssign. So there's a car of mass 980 kilograms moving at 20.7 meters per second. There's a truck 1500 kilogram moving at some velocity which we don't know. They both collide and then they combine or move as one unit because they stick together, and that combined wreckage moves in this direction. We know that the final momentum has to be in this direction because total momentum is always conserved. So an east momentum vector and a north momentum vector will give you something in the northeast direction. So let us apply momentum conservation in the x direction. So along the x direction, the initial momentum of the car is 980 times 20.7. You know, momentum is mass times velocity. The truck has no momentum along the x direction. In this is our x. So there is no momentum of the truck along the x direction. So plus 0 equals. We want to know what is the final momentum. Because these two are now behaving as one unit, there's only one term on the right hand side. And so this is the velocity of the combined wreckage, which is labeled as VF. So the momentum vector will be here as well. So just for clarity purposes, I'm going to draw the vector a little bit bigger. So then you can split this into the x and the y direction. So if this is my momentum vector, this is my px and this is my py. And this angle is given to us as 41. So therefore, if you only want the x momentum, that means you take, this will be the mass times your px, and this will be your mass times your vy. So our vx is going to be vf cosine 41, and our mass is going to be the combined masses of the two because it's the unit is both masses put together. So it's going to be 980 plus 1500 kilograms. So rewriting this equation, you get 980 times 20.7 equals 1500 plus 980 will be 2480 VF cosine 41. So from this equation, the only unknown is VF, so you can solve for VF. Solving, we get VF as equal to 10.8 meters per second. So that is the velocity of the truck before it hit the car. But we still want to know what is the final velocity of, that's the velocity of the combined wreckage after the collision. But we still want to know what is the velocity of the truck. And so that means we need to look at the y direction. So to applying the conservation of momentum principle to the y direction, the car has no y momentum, so therefore the y momentum of the car is 0, plus the truck's momentum along the y direction is 1500 times its velocity, which is our unknown, equals the combined wreckage. It has a y momentum of m times vy, and we know that the mass is 2480. And then the y component of the velocity will be vf sine 41. So therefore that equation simplifies to 1500 times vt equals, we already know that vf is 10.8, so therefore we can write 2480 times 10.8 times sine 41, and that allows you to solve for the velocity of the truck. And the velocity of the truck comes out to be 11.7 meters per second.